Hello, welcome to our low-temperature thermochronology online lectures. I'm Anita from the School of Earth Science and Resources. You are welcome to scan this QR code and it will direct you to my university homepage where you will be able to find more information about our lectures. Today, we'll be continuing learning Chapter 9, the Thermal History Reconstruction of Sedimentary Basins. Last time, we have been gone through some terms and basic approaches, and today we'll be learning Section 2, Modeling of Thermal History by Hefty Program. So, first thing first, what is Hefty? Hefty is a very popular modeling program which can allow us to model the helium, fission track, and other thermochronological data. Where is Hefty? Here is the address where you can always get the latest version of this program. The next question comes to us is, why Hefty? Or what is Hefty good for? Well, Hefty is normally used for forward and inverse modeling of low-temperature thermochronometers, including fission track, helium, and the data we can input including abated fission track ages, abated fission track length, uranium thorium scenario helium data, as well as vitrinite reflectance measurement data. Hefty is also good for teaching. As we are using here, it is a good teaching tool to show people how to do basic thermal history modeling. It is also a system that is very friendly for us to explore. It allows us to run model interactively side by side. We can change parameters easily, and we can easily compare the different results. The difference between forward and inverse modeling is probably the forward modeling is a supervised one, whereas the inverse modeling is conducted automatically by computer, or it is unsupervised. Nevertheless, both for forward and inverse modeling, we need to prepare the input data, initial conditions, selection models, and do the modeling, and to test your result. Here is a model of track length recording thermal history. To understanding all these basics will help us to learn how the modeling program do the modeling process. So, how Hefty do AFT forward modeling? Here, AFT is short for abated fission track analysis. Given the time temperature history, calculate the age and length distribution. The time temperature history is divided into some small time steps. Then, the program will generate a set of track length populations in each time step, according to the duration of the step. Anneal each population through subsequent thermal history. Combine the population to get length distribution, accounting for varying probability of observation. And finally, the program will sum age contribution for each time step, using conversion from the length to density. In these slides, we will show the basic rules of how Hefty do inverse modeling, a preview. Different from the forward modeling, for inverse modeling, strategy is posing candidates' thermal histories. It is a statistical comparison of model calculations to measurements, and it is a way of parsing and displaying results. This figure to the right shows us the window in the Hefty program, displaying the track length distribution and the modeling result of time temperature histories. To understand that figure, we need to have a brief understanding of some statistics in Hefty program. First, all of the statistics are based on estimation of uncertainty, which you provide as your input data, and the evaluation of misfit relative to the uncertainty. In detail, this result in expectation could be expressed as C1 equals to everything influencing your observation: the thermal history, measurement details, and calibration issues, etc. Hefty assumes known uncertainties predominant. Different tests for length distribution, age, etc. And in this figure, we can see that the model result contains the blue color time temperature histories and the pink color time temperature thermal histories. So what are the pink and the green curves mean? The pink means good ones, where the expectation is about 0.5, means that expected result if absolutely everything is correct. While the green ones means that acceptable, where the E equals to 0.05 means that it doesn't fill the 90% confidence test. However, all this is based on a critical assumption that all uncertainties are well qualified, which is not always the case, unfortunately. Kinetic variability can be detected in many ways. For example, here, by plotting the kinetics, dPAR, and the chlorine contents with appetite efficient track age and length data. There are many possible kinetic proxies, and the commonly used ones include chlorine content, dPAR, unit cell parameters, and a combining factor incorporating all composition factors. The vitrinite reflex data can be taken into account in Hefty program, and there are two models of vitrinite reflectance in Hefty: EZRO and IKU. EZRO is higher if peak temperature below 180 degrees centigrade, where the percentage of vitrinite reflectance is about 1.6, and IKU will give higher values when temperatures are above 180 degrees centigrade. EZRO model allows maximum value of 4.69, whereas IKU max value is 8.17. Thermal modeling must be preluded by a review of geological events and their thermal consequences. These dates can be the turning point of the thermal history and thus temperature constraints of the modeling. In these slides, we show the relationship between the stratigraphic age and appetite efficient track age, and how to analyze and interpret this age data. When stratigraphic age is way older than appetite efficient track age, we say sample is reset and could model as cooling only, or use vitrinite reflex data for maximal barrel temperature estimation. When stratigraphic age is similar to appetite efficient track age, sample may be partially reset and records reheating information. Reheating is particularly likely if length shorted. When stratigraphic age is much younger than appetite efficient track age, sample is not reset and records provenance information. Therefore, we need to look for populations and try various kinetics and bimodal fitting, which is frequently the case for zircon fission track data. Multiple provenance is tough to handle with Hefty program, where it assumes a single temp temperature path. How well can we pin down some aspect of the thermal history? That is the key for temp temperature modeling. Shape of cooling path, for instance, can be constrained by the number of track lengths measured. Calibration of length data. Peaking reheating temperature depends heavily on annealing kinetics, such as dPAR and chlorine content. And our knowledge here is incomplete that even fluorine apatite has a 10 degrees centigrade range of annealing temperatures. Therefore, uncertainty increases with increasing resistance. Neither dPAR nor chlorine content are perfect, so multi-compositional may be the best. And the time of peak reheating or initiation of cooling should be considered with the combination of length and other information such as age, which is often a trade-off, however, as there are a range of solutions. Biasing among length populations can leave an effect and can be analyzed dependent. Multiple samples will help in some of these cases, however. And there's another interesting question. What set of thermal history is compatible with my data and my assumptions? It is critical to have a hypothesis in mind and add as much geological information as you can. Rule out stupid histories that is not consistent with geological observations. So modeling is actually a process of think, adapt, and involve. Have fun. To determine the specifications of inverse modeling, the temp temperature modeled path must pass throughout the boxes of the constraints. So, two key questions: where to put the boxes and what happened between the boxes. Here are some principles for the placement of the boxes. For the final condition, it is normally the present-day temperature, whereas for the initial condition, it should be above the total annealing temperature zone. When we are modeling the history of sedimentary samples, stratigraphic age is adopted for the deposition age. And when we are modeling the temp temperature history of granites or other igneous rocks, the intrusion age and depth should be considered. Residence and reheating should also be considered when you are putting your box. Please be reminded that the results are often non-unique. Each constraint is essentially a part of your hypothesis, so be careful when you are putting every constraint. Resolving ambiguity using multiple samples is sometimes helpful. Here, the cooling-only reconstructions is incompatible at 60 to 50 million years. But the modeling of the reheating scenario reconstruction is compatible with both samples. So, here comes the question: how much complexity is complex enough? To answer this interesting question, we model a case starting with only the simplest solutions allowed. We can see that very nice temp temperature thermal history has been yielded by the software. Then, we are trying to add in one more degree of freedom to make the history a little bit complex. And we're continuing to add one more degree of freedom. And here is the modeling result of the temp temperature history. By comparing the more complex scenario with the simplest scenario modeling, it is now realized that adding too much freedom is not always bringing us the better results. So we should be cautious about freedom and not more strings better. The above is all we have for the Hefty program. You are always encouraged to do the modeling by yourself. The more practice, the better results. Thank you for your attention.